Hey everybody. It feels like it's been a while, but that's probably just due to the week 10 assignment. Hopefully that went well. I've received quite a few of your submissions already, and from what I've seen, a lot of them are really good. So great job there. Hopefully it's again been a little bit of a break from our normal kind of productivity. Now we're going to dive right back into some of the course content, and it's a little bit different because why not? So this week 11 is water part one. So this is the only time that we're going to have some kind of overlapping information, both from this test and the next test. However, I'm going to try to give some guidance on that throughout it. We still don't have overlapping content as far as questions go or specific content, but again, we'll address that here in a little bit. So whenever we're talking about water, we have a few topics that we're going to be specifically going over and that are important for you to be able to understand overall. So the hydrological cycle, otherwise known as the water cycle, surface water versus groundwater, both pros and cons of each, well characteristics, waterborne diseases, bottled water, and drinking water systems. Now, the reason I put drinking water systems on there is because that is in your readings. However, we're not really going to be going over drinking water systems according to this test, but it's on week 11 because if you have time, look at it. It's going to give you a really good refresher as there's a typical flow that drinking water goes through for the purification process. And so if you're able to have time to look at it now, it's able to help out next week whenever we're starting material for the fourth exam. So again, drinking water systems, not covering it really this week, or it's not going to be on this exam. However, if you do study it, it's going to holistically, it ties in with all the same material, and it will be on the next exam. Just want to give you a little bit of a heads up. So first, water. One thing I wanted to be able to talk about is this picture right here. Sorry, I thought about typing it out, but I think just this picture really summed it up the best. So I'll try to describe the picture the best I can. It's a lot of different charts, a lot of different diagrams, and we'll start over here on the left. The one thing that we can be able to see, this chart right here, this 100% chart, just describes the total global water supply. As we can see, this estimates about 96 to 97% of all water on the planet Earth is captured within the oceans. That's all of your salt water. A majority, large majority of water on Earth is salt water. It's not water that we can readily be able to utilize or readily be able to drink. And so up here, if we look all the way up here, 2.5%, that's fresh water. That's everything that we can be able to find, whether on the surface, whether in the groundwater, whether captured in glaciers, all of that we can actually use for actual drinking water in its current state. It then takes that 2.5% and splits it up even more. This next 100% diagram just looks at fresh water. How much of fresh water is what? We can be able to see that 68, almost 70% is captured in glaciers and ice caps, whereas 30% can be found underneath the ground in groundwater. And then 1.3%, that's your surface water and other fresh water that could be present on land. And it dives even further into this other 100% column chart, surface water and other fresh water. That breaks it up into 73% at one time is ice and snow, 20%, you find that in the lakes. Then it goes even into smaller ones such as atmospheric water, biological water, rivers, swamps, soil moisture. Again, the overall premise is captured here on the right. All Earth, all water on Earth, roughly about 99% of it is unusable. Water that's usable by humans, which is only about 1%, is mostly groundwater, where some are then lakes and rivers, otherwise known as surface water. So it's so very important. It's a very, very small fraction of usable water that we can have. That's why water conservation and protecting water supplies are so critical. Just whenever we're looking at ratios of the earth, still, in a manner of speaking, that's a ton of water. Still, everything that we can use. However, it just brings that further emphasis. So majority of water, salt water, but we're going to be focusing on the water we do use. So that brings us into the water cycle. Most likely you may have learned this during 5th grade. I believe we've already gone over this a little bit, but we're just going to go over a few keywords with this. This picture here on the right perfectly describes it, but all of the words on the left just demonstrate all the different steps that water goes through. So we're going to be starting with just water that's on the surface, for example, in a lake or in a stream. It could go through the evaporation process. So from oceans, lakes, and streams, water is evaporated. Evaporation means going from a liquid to a vapor. And same thing, transpiration, that's where water within plants turns into vapor and is given off. This evaporation and transpiration, these water vapor, goes up into the atmosphere and it condenses. It's condensation. That's where water vapor turns into a liquid. And after a large accumulation of that water vapor has accumulated together underneath the right conditions, that's whenever precipitation occurs. That's whenever water travels from the atmosphere back to the ground. That could be whether in the form of snow or most commonly in rain. As we commonly hear like a weatherman talking about precipitation that might be going on, it's just that water now coming back down to earth and to the surface. Then, whether it's rain or whether it's melting snow, that contributes into surface runoff. That's just further traveling of that water until it can be able to settle into the ground. And whenever the water does settle and reach back into the water table, that is otherwise known as groundwater. So water below the surface of the land. Very simply, that is the water cycle. It's important just to be able to know some of these key words as they are important just how water travels throughout this cycle. So first, let's go into what is surface water. So surface water, very simply, lakes, ponds, rivers, streams. If you can see it, it's surface water. Almost as simple as that. Some key characteristics of surface water are that some pros, very easily accessible. Honestly, you could just go right down to a river, grab a bucket, you can get it. That's it. It's also easily quantifiable. We can know how much that we have just by looking at it. That's it. Everything that we can see, we know it. Some cons of surface water, and again, this is under the perspective of imagine if we relied on surface water to get our drinking water, our usable water. So again, pros, easily accessible, we can get it, and we know how much it is in case we're close to running out. Cons is that the evaporation loss is significant. It's right there underneath the sun. It can be heated up very easily. It's going to evaporate very fast. Same thing, aquifers must be recharged. It takes time. Again, aquifers, you can think of storage places. So a pond, over time, it's going to dry out if it doesn't have a constant feeding mechanism into it. And that can sometimes take time as well. That's where we find a lot of locations that are drought prone. That's what sometimes they run into, is that their aquifers on a surface level, they run out very quickly. And it's also easily contaminated. Anything can just walk right in and contaminate it, or it could be dumped right in, or dumped right next to it, or dumped upriver, and now it travels down to the pond and it gets contaminated. Surface water, since it's right there, it's very accessible. It's also accessible to contamination as well. Next, groundwater. Yep, I'm not blocking anything really. Okay, groundwater. So groundwater is any water that is underneath the ground. Very intuitive that they decided the wording for this. So although spring water is considered the purest water, it's not always the case. So it's more common that groundwater is going to be cleaner. It's not easily as contaminated. It also contains natural filtering mechanisms just above it. So right here in this picture, you can be able to see a water well, and it kind of demonstrates how it's able to be a little bit into the earth, but it's still fairly shallow. But then, for example, a driven or a drilled well, such as this artesian well, is able to go much farther all of these different layers of the earth actually act as a filter. We're going to be going more into how it filters next week in that next material, like I talked about. But just know that a lot of these different things, sand and gravel, loam, clay, these various different substances, not really clay, I guess, but they can be able to act as a natural filter as the water is trickling down and trying to reach that groundwater or that water table. So if you're using groundwater, it's not very easily contaminated and it can contain some of those natural filters. Some downsides to it, it's not easy to access. Not everyone can be able to build a well very easily, or as well, um, get down to maybe a necessary water table that could be 50 to 100 feet deep. That's pretty hefty, and that's even out of the reasonability of digging down that far, just manually. It can potentially be full of minerals. That's what we typically refer to as hard water. So if you have hard water in the state where you live, that's mostly because during that filtration process, it's going through the dirt and through all the soil and gravel and things of that nature. It's picking up minerals as it goes. Are those minerals good or bad? It just depends. But it is creating harder water. That's harder on our pipes, not internal, not our body pipes, but hard on our like housing pipes, and that can be just that natural buildup. So again, some pluses and minuses to both surface water and groundwater, but it's important to be able to know the difference between the two. Next, waterborne diseases. So this one is a fun one. We're talking about waterborne diseases, and you're going to see a lot of very similar ones and ones that are related. So most common thing whenever dealing with waterborne diseases is that they're typically all through the fecal oral route. Again, fecal oral route, what that means is that an animal or a person's feces are somehow getting into the digestive system of another animal or human. Therefore, it's causing this cycle of that constant virus, bacteria, or parasite regeneration. So just a quick fact with that, annually, waterborne diseases cause nearly 2 million deaths. And same thing, about 4 billion cases of diarrhea are caused just by waterborne diseases. 9 out of 10 deaths are within children. So it's highly, highly susceptible in children, something very, very easy to watch out for, especially because whenever we're looking at diarrhea, one of the biggest problems with that is just with that factor of dehydration, losing liquid very fast. That's why it's very, very bad for children who don't have a lot of fluids in them to begin with. And it's also a lot harder to be able to hydrate them in some instances. And the shocking thing, or the really scary thing, is that this is virtually all of these deaths and these cases are typically always within developing countries just because of infrastructure and just because of availability of water present and how easily sometimes that water can be able to be contaminated. So up here or down here in the lower right, it's just a picture illustration showing as far as someone using an outhouse. Doesn't show too much, don't worry. But as that stuff is accumulated here in the bottom of the outhouse, that can naturally be able to leak into the soil if it's not properly encapsulated. And then it shows this individual drawing water out of a nearby well. It very easily can transfer in that simple of a manner. Or even just someone going to the bathroom upriver of where you might be swimming or getting water downriver. Some examples of waterborne diseases, and definitely look at the readings. These go into them a little bit more, so I'm not going to go into them, but I'm going to at least reference them. Here's some examples of waterborne diseases, some of the most common ones that I hear about. Cryptosporidium, Giardia, that one's a huge one as well. Shigella, E. coli, and Legionella. So these are a variety of different things, whether they're a parasite or a bacteria or a virus. Waterborne diseases can be everywhere. This top right picture illustrates another very common way that individuals get sick. And that's why if you're a parent, some of the biggest guidance and direction, if I were to offer it, is if you go try to avoid taking your kids in that try to avoid taking your kids that may be too young to avoid getting water into their mouth. But then as well, always make sure to wear a swim diaper with your children. Cryptosporidium back, I believe there's something in the reading about this. If not, I'll share it right here. Back in the early 2000s, there was a cryptosporidium outbreak here in Utah that it plagued quite a few different or several different pools here around in the area. And one of the really dangerous things about cryptosporidium is that the parasite itself that causes that disease, it has a capsule or a shell around it. And this has been developed and cultivated and mutated over time. Well, one of the biggest things that pools and other water recreation places typically do is they spike pools to be able to help kind of kill some of the bacteria and the viruses and such. However, Cryptosporidium, because it has that shell, it's a lot more resistant to it. And so with that and cultural practice of not many people actually putting their kids into swim diapers to help capture poop, because let's face it, babies and kids, they poop, it's everywhere. um, it caused a pandemic within the area of that outbreak for a few summers. Now it's definitely calmed down, but it definitely is something to be aware of. This isn't just water that we're intentionally drinking. It could be water that we're just exposing ourselves to that we could still be affected by. Next, let's quickly go over bottled water. So some of you may really like bottled water. I personally, I'm more of a drinking out of the tap person, just from where I was raised. But either way, it's important to be able to understand some key things about bottled water. So one of the biggest things is that a lot of them, a large majority of bottled water as we typically see it, I believe Smart Water, Aquafina, those are the only two that come to mind right now. For the most part, they're just tap water. That's really it. You can be able to look it up. Actually, if you have some time, I would suggest looking it up. It's actually pretty interesting. Bottled water in any essence. But for the most part, it's all tap water. It's not captured from somewhere really exotic and then filtered and transferred over. It's just filtered tap water. Bottled water is regulated by the Food and Drug Administration. I say regulated very lightly because it is very minimally regulated. It's actually shocking how non-regulated bottled water is. For the most part, the FDA does require certain filtration standards to be in place for bottled water. It needs to be filtered and it needs to be pure in that sense. But with that being said, the unregulation of it, not unregulation, there's a better word for it, but the lack of regulation that is present within bottled water really has to do with some of these key words. So, for example, like mountain spring, like mountain spring water, or natural spring, or reverse osmosis. Some of these big like catchwords that they use, a lot of them don't have definitions behind them, or a very loose definitions that could be behind them. For example, if I remember right, mountain spring water doesn't mean that they hired a Sherpa to be able to go up to some exotic mountain and they carry it down in buckets so that they can then pour it into your little water bottle so that you can be able to buy it in your local Walmart or Piggly Wiggly. It's not that. So for the most part, like mountain spring water, if I remember right, it's any water that is collected within, it's like 25 miles from the base of a nearby mountain. That's a pretty big range. Like I'm right here where I'm located in Kaysville, Utah. I'm about 25 miles away from a mountain. I would not consider this mountain spring water, but it falls under that. It's just highlighting that it's not really a very regulated industry. A lot of these terms that people could use. Now, reverse osmosis, before you get on to me, the only reason I put that on there is because a lot of them go as far as saying like, oh, it's reverse osmosis because it sounds very fancy and very cool. It's a filtration process, and it's pretty good, but it just basically means they ran it through a really, really small filter, and that's it. Just they ran it through a filter. So I believe that studies have found that the purest water, if you were to try to find like what is the most pure water, it's actually finding water that's distilled. And so distilled water can be that distillation process. But again, we don't really go into that for pottled water for the most part. Just know a lot of it is just tap water. A lot of it's just plain water. But if you like the taste, if you can be able to afford it, if everything goes well, more on you. But it definitely takes some precautions. One of the biggest ones that I will, unsolicited advice, is do not keep bottled water like these bottles or any plastic bottles in your car or any hot location. Try to avoid it as much as possible. Studies back in like 2008 as well identified that plastic can be able to leach from the water bottles into the water that you are now ingesting. Plastic ingestion, plastic, microplastic exposure is a huge issue. If you want to go into it, just let me know. I love talking about that stuff. But just further things, yeah, again, unsolicited, not on test, but it's cool. Okay. All right. So now we're going to be talking about our very final topic. I know we went by pretty quick, but you've reached the end. And well, 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 we're going to talk about wells. Yeah, I did that whole slide for that one joke, so hope you laughed. If not, that's okay. Just don't tell me you didn't laugh. Okay, so wells. So we're not talking about Nevada. We're talking about ways that we can be able to access groundwater. And so most common way to access groundwater aquifers or storage locations is through the use of a well. So some examples of those wells include dug wells, driven wells, drilled wells, wishing wells. Not really, not wishing wells. That's not the same thing. That's a money grabbing scheme, if you ask me. But when a well is created, a bacteriological analysis should be performed. Anytime that you build a well, you should be able to analyze it, and you should look at it. Most commonly, if you're looking for bacteria, you're testing for coliforms. Coliforms, very easily, bacteria always present within digestive tract and feces. Again, those waterborne illnesses, that's where we're finding. They're from that fecal oral route. You're wanting to test it for that to be able to make sure that we're good. And so with wells, again, three of them that we're going to highlight. There's a lot of other kinds of wells, but these are the three big ones that I'm going to go over during this time. And I do apologize very quickly for, I re-looked at the readings. There's not a lot about this, but it is on the test, it is on the quiz, so I'm going to try to equip you with all the information that you're going to need. But let's go into these ones very simply. A dug well, a driven well, and a drilled well. They're all to be able to access groundwater. However, there's some unique characteristics that make them good and that make them bad, and some, sure, it just depends on the situation. So a dug well. Typically, a dug well is less than 15 feet deep, is not very deep. And if you look over here on this picture, the left side of the picture illustrates a dug well. You can be able to see an individual inside of the hole itself just with a shovel, another individual helping to be able to carry out these loads of dirt. Imagine that. Imagine digging into the ground to then remove the dirt so that then you can be able to reach the water table and what you need. It makes sense why these are typically less than 15 feet. They're not very deep at all. And as well as they can be very easily contaminated, not only by the individual that's there, but typically they have to be left just wide open and anything could be able to potentially fall into it. Same thing, sometimes they have to build out instead of just straight up and down, because how in the world is that guy going to get out unless he's riding the bucket up? And that could also just further promote that kind of wide funneled out, can be able to promote more things falling into it and further contaminating the source. So easiest to contaminate dug wells. Driven wells is this middle picture right here. Those can reach typically 30 to 50 feet. They are created through, as you can be able to see, there's a great illustration of it. Think of it kind of like a pencil, as far as a pipe with a pointy end on the end of it, so that a large weight can be risen and then dropped, so that it can pound or drive this pipe into the ground, and it's physically pushing away the dirt. Now, this can be very useful, but it just depends on how deep the pipe is. But then, as well, what can they do without risk of bending or breaking the pipe? Because if they get it down 50 feet and they hit it and then it breaks the pipe, now the whole entire pipe is useless. So it's a little bit better. It doesn't have that opening, so it's less contamination would get in. However, it's yeah, that's about it. That's a driven well. Next are drilled wells. So drilled wells, those ones 100 to 800 feet deep is about average. Some can even be more than 1,000 feet deep. One of the reasons why is here on the picture on the right side, it illustrates a drill going down. This typically includes as far as a drill bit and a bored tube, so that as it's drilling down, it can constantly be filtering dirt up and it can just keep going as far as it needs to. This is the least likely to be contaminated. There's not a lot that can be able to fall into it. Almost nothing can be fall into it. Typically, the contamination, if it is present, may be minimal from the drill itself, or was already existing within the aquifer or within a layer of the soil that was already present. But those are the three different types of wells that are really important just to be able to distinguish: just dug wells, driven wells, drilled wells. Dug wells is the easiest to be contaminated because it's so shallow. And drilled wells, it's the least likely to be contaminated because it can be able to go so deep without opening up the possibility up at the top for contamination to occur. And ultimately, that's really it. Really, hopefully it was kind of quick. Definitely utilize the reading resources to be able to go over those waterborne diseases a little bit more. Hopefully this video can be able to help you out and kind of succinct what you need, and that this was a quick hit right before the exam. Definitely let me know if you have any questions. Hopefully the week 10 assignment went well. If you have any further questions about that, please feel free to reach out. As always, thank you guys so much, and I hope you have a great week. And if not, just make it a great week.